Hello. You can drop a text in the chat box as well.
Yes, sir, you are audible.
Yeah, great, great. So, yeah, welcome everyone. We'll just wait for 5 more minutes for everybody else to join, and then we'll start with the session. Yeah. Yeah. So now that enough of us are here, let's begin the session. Um, First of all, I just want to know, like, how is everybody doing? See,
Absolutely great, sir.
good, Prasad, good. So amazing. Uh, Let me tell you about the session. Okay, so it's about cryogenic engine, how it functions, and what are the possibilities, and what are the challenges with it. And Towards the end of the session, I'll share a form link which you guys can fill. You can avail a counseling from that, and accordingly. Throughout the session, if you guys have any questions, any doubts, you can put that in the chat, or you can also unmute yourself and ask. Okay. So without any ado, let's just start with the session. I'm presenting my screen. You guys let me know if it is visible or not. Yeah, my screen is visible.
Yes.
Cool. So today's topic, cryogenic engine. I'm just going to talk about rocket propulsion, fuel and oxidizer. What are these concepts like? What is the concept of specific impulse? How it impacts the propulsion? Then mechanical design aspects of the whole thing. Uh, and towards the end of it, we will see why is it difficult to create this specific engine, and to what extent people have been implementing, and where specifically people are using these kind of engines. Okay, so the biggest or the basic challenge you guys can tell me in rocket propulsion is what is the biggest problem with rocket propulsion, as you can see uh, in this. Like, can you tell me? Can anybody tell me? According to you, it can be anything. Your opinion, like, what is the problem? Like, why do we need special kind of engines? Why can't we use just our IC engines?
Because the it's depend upon the payload. अगर payload बहुत ज़्यादा है, if the payload is very high, for example in terms of kgs and ton, then equally amount of thrust we require. As mentioned here, the action and the reaction. So we need equal action to accelerate that payload into the low Earth orbit. So I think that is thrust is a major challenge in
Mhm.
appropriate uh, size of engines.
Okay.
Some,
Yeah, that's a good point. Go ahead. Somebody else is trying. Yeah.
yes, sir. Yes, sir. By using IC engine, the out of force, if we place our hand in the exhaust, the force is not that much to lift the rocket high, sir. So that's the reason we are using rocket propulsion and some cryogenic chamber, so and so, sir.
Yeah. Great.
And
Uh,
IC engine requires oxygen for combustion. And जैसे as rocket size increases, then oxygen level will be decreased. So we need different kind of system for rockets. I think so.
Even rocket engines uses oxygen, sir.
mhm. Yeah. Keep them coming. Anybody else would like to share?
Rockets use liquid oxygen, right?
I'm sorry, I didn't catch that.
We actually need cryogenic engine so that we can get better thrust to the engine
Okay.
for the rocket, so that it can go. So I can reach that supersonic level. Like it can break the sound barrier of the atmosphere.
Great. So all of you are correct. All of you had some interesting ideas. Like, the basic and the biggest challenge is to produce sufficient amount of thrust to resist the amount of weight the rocket has, like creating equal amount of action or reaction to the action that it is creating uh, on the surface, right? To counter the weight. Now, to do this, uh, the first and foremost thing that needs to be taken care of is fuel, right? Do you think the regular fuel that we use in our regular transportation systems is sufficient to
No,
fulfill the, yeah?
no,
Uh,
sir. We use H2O, sir,
okay. Why is it not sufficient?
because the amount of here in IC engines we use petrol with octane number and cetan number, but just for the combustion process. But when we compared in the rocket, it accepts the thrust and the efficiency with the fuel burns and the thrust it produces.
Correct, 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 correct. The biggest, like the basic idea. Yeah, go ahead. Somebody was saying something.
Yeah. So in a rocket engine, we use the special rocket grade kerosene RP1, and some rocket use the oxygen, hydrogen, and some methane. So IC engine use the petrol, but petrol has lower calorific value compared to a rocket grade kerosene.
Okay.
So that's why, and to get higher thrust, we need higher fuel ratio.
Exactly, exactly. Anybody else would like to say something?
And even sir, we mix petrol with some parts, sir, like stoichiometric part 19 is to 1 ratio, such that 19 parts of air and 1 part of fuel. And here in rocket, I don't know what part we use, but there might be some changes.
Exactly, exactly. Now, with the fuel, right? The basic thing with the fuel is you need to have a fuel which is which should be able to generate enough amount of thrust. Okay, so if basically, let's say this is your rocket, then thrust is being generated at the expense of momentum loss. Okay, the more amount of momentum you lose, the more amount of thrust you gain. So that's the basic. That's the basic concept. Because you need to have yeah. Anybody wants to say something? Okay, never mind. So basically, you need the thrust that you're going to generate is going to go at the expense of momentum loss. Similarly, when you burn the fuel in the chamber, like combustion chamber, the rate at which the exhaust goes and the rate at which it goes out is also a determining factor in order to generate the amount of thrust, because the faster the exhaust gas is moving out of this exhaust chamber, the higher amount of thrust you're going to generate. Okay, so that's the second part. And the third thing that you need to take care of is speed is directly proportional to temperature in this temperature of your exhaust gas. Okay, so the higher amount of temperature you have of your exhaust gas, the more amount of speed at which it will get exhausted, and that will reflect in generating ample amount of reaction force, that in the form of thrust. Okay, so three things: you need to generate maximum amount of thrust. It depends on momentum loss. Second thing is you need to have your exhaust gas should burn at a rate at which it is getting exhausted at a higher rate. And ultimately, the speed is also a function of temperature. If your exhaust gas is having higher amount of temperature, automatically it will have higher amount of speed while it is exhausting, and accordingly you will get higher amount of thrust. Taking this concept, taking these criteria, one term comes into mind, which is specific impulse. Does anybody know anything about specific impulse, what it is? Anybody wants to share?
Don't know, sir.
Okay. Okay. So specific impulse basically is the amount of push the rocket gets by burning per unit of propellant. Okay. To understand this concept better, we'll first understand what is a propellant. Okay. When you go to such kind of engine, right? You have this. Let's say this is your not this. Okay. This is your combustion chamber. This is your engine. This is your engine compartment basically, and this is where the exhaust gas are burning and getting exhausted. Okay. This is a generic idea of a cryogenic engine. Okay. Very, very basic drawing. Okay. I'm not good with drawing.
Sir,
Yeah.
cryogenic means, sir?
Cryogenic means you're operating at a temperature which is well below your normal temperature range. It's like negative 250 degrees or something. So that's what cryogenic means.
Yes,
So
sir.
when you're operating at very, very low temperatures, basically that is what it is. So I'll tell you about like why do we call this specific engine cryogenic engine? Okay. Basically, you will have your fuel and you will have your oxidizer, because of course you need to burn fuel, you need oxygen for it, right? Now, if you take a fuel in its direct format, let's say if you take liquid petroleum for instances, it doesn't have the high amount of calorific value to burn at a rate which it will not be able to generate the enough amount of thrust that is going to be pushing the rocket in the air. Okay. So what we need to do is we need to use a fuel which is having high specific impulse. Okay. In that means that basically you need to have your propellant need to have a burning capacity per unit propellant need to have a burning capacity which can generate enough amount of push, like to be able to push the rocket in the right direction, and that's how the whole this thing decided. Now, if you use your normal fuels, you will not be able to generate that much amount of thrust. So you will use hydrogen, either you will use methane, or you will use RP1. RP1 is basically refined petroleum. Okay, so while you're using these kind of propellants or these kind of fuels, you'll also use oxygen. Okay, so that's your oxidizer. This is your fuel that is going to get burned. Okay, and with the with these propellants, you need to have high amount of calorific value. You need to have in order to burn it at a significant range. So if you talk about like okay, if you talk about burning your fuel in this, if you talk about like this specific impulse kind of a form, basically it means that at which at a particular significant point, the amount of heat, the amount of energy it exerts while burning. Okay, that's the measure we use for basically the more amount of energy it will generate and the more amount of thrust it will produce. So that's how the trade-off goes. With methane, this thing also depends on the molecular weight of the fuel that you are going to use. So you will have you often see that a fuel that is having less molecular weight, whatever, the fuel that is having less molecular weight and the fuel that is having more calorific value will be the ideal fuel for this kind of operation. Okay, will be ideal for this kind of operation, this kind of usage. if you use hydrogen, if you use methane, and if you use RP. So hydrogen among these three would have the most amount of specific impulse, which due to its higher calorific value compared to these two fuels and due to its lower molecular weight. So it has like 2 grams per mole molecular weight as compared to CH4 and RP. So due to this exact reason, you're using hydrogen. Now, if you are using hydrogen at normal temperatures, your hydrogen is at in a gaseous form. And if you want to use hydrogen at normal temperature, you will need bigger tanks to store that hydrogen, right? So if you are using bigger tanks, you are unnecessarily putting it too much amount of weight also larger. You are making the size larger also for the aircraft, right? For this particular thing. So there comes the need of compressing the hydrogen, and there comes the need of liquefying the hydrogen. Okay, so for hydrogen liquefaction, essentially there are a lot of hydrogen is put through different stages. Like there will be a series of compressors, then condensers, then there are fuel processors, which basically turns this hydrogen into its liquefied state. Now, when you look at the liquid hydrogen, it is at a temperature of negative 253 degrees Celsius. So when you are operating at minus 253 degrees Celsius, this concept becomes cryogenic because your fuel is at that lower of a temperature. This is being done to reduce the tank size. Now, once you have compressed hydrogen, liquefied hydrogen, you're operating at like, let's say 13 bars or 14 bars of a pressure. When at times that pressure increases to 52 bars. So that is basically, that's the fuel that you're going to use, and that's the fuel that you're going to store. Apart from that, same thing is being done with oxidizer, like oxygen. So basically the structure goes this way. I'll just erase some of the things. Okay, the structure goes this way. So this is your tank, in which there is this one tank, there is this second tank. Okay, this is your hydrogen, this is your oxygen, this one. Okay, and this is the outer shell, which protects these two tanks. And in order to protect this outer shell, because this is going to be in contact with atmosphere and it is going to have higher amount of heat generated over its surface, so there is a coating provided of a material which basically protects, which basically thermally insulates this tank in order to avoid the material damage. Okay, so once you have these particular tanks, so there are such two kind of tanks. So basically, two tanks are usually you see. So if you look at this propeller closely, okay, you have this somewhere you have this this red particular tank that you're seeing. That is the single tank that you have. Then there are these two propellants, which are propellers, which are basically launch pad vehicles. So basically they are helping this whole assembly sustain the flight or basically get into the atmosphere. Your actual engine, the cryogenic engine, is over here. Okay, so if you are seeing that these are the two exhaust systems, so then there are two cryogenic engines. Okay, so when you see this particular red tank, that is this fuel storage tank, which basically used to store the fuel. Okay, now seeing that the storage and everything, learning about the specific impulse, let's talk about mechanical aspects as such. Now, when you talk about the cryogenic engine application, there is an engine, there is a like burning chamber, exhaust gases exiting, and like a supply chain, basically how the fuel is going to supply it from the tank. So let's say this is a tank, this is the engine, this is the chamber. Then how the fuel is going to get supplied to the engine, how the engine is going to burn the fuel, how the chamber is going to handle the scorching heat and produce the exhaust that it's needed, and how these things are going to work from a perspective. Okay, so you have can you guys tell me, let's say this is a tank and this is the second tank, okay, and from here I'm trying to push the, let's say this, okay, I'm trying to push these two into the engine. Okay, so this is your hydrogen, this is your oxygen. So first of all, can I do it directly? So can I directly inject hydrogen and oxygen and combust it and hope for the...
No, sir. No, sir. By using a pump, sir, because we need to maintain proper process.
Okay. Can you explain that just a bit?
By using something mechanical pump or some means of pump such that the it's in human control. The reaction process is in as humans control, sir. Without pump, we don't know how much amount of O2 and H2 will be going into the engine.
That is one aspect, okay. Other than that, the biggest challenge is if you directly inject hydrogen and oxygen, due to them being at that condition, at that high condition, don't know how they're going to combust. You don't know how the reaction is going to proceed, as he said, and you won't have any control over it. You might even have a material damage. So for that, you can't directly inject oxygen and hydrogen into the engine. You need to have a regulatory system. So what kind of regulatory system are we talking about? So first you need to then pump the fuel into the engine. Now, if you are using your hydraulic powered pump, like the motor that you have at your home, do you think will that motor be feasible? Do you think we can use that a normal regular pump that we use to pump this fuel?
No, sir.
Why?
Because electrical components and efficiency will be at high stakes, sir.
Exactly.
Even weight also.
Exactly. Apart from that, not even going to that, the amount of power that electrical pump is going to need, you need to supply electricity. How are you going to supply electricity, right?
Yes, sir. Yes, sir. Yes, sir. But we can implement mechanical pumps, sir. Piston, something like that.
Yeah. So there is this concept to tackle this biggest problem. Like we can't use electrical pump. So what we can use mechanical pump. So one such example of a mechanical pump is something which is driven by a turbine. Okay. So let's say if this is your pump and this is your turbine. This turbine is basically being operated or rotated to regulate the pump. Okay. So how do we operate this turbine? Can you guys tell me? Let's say this is a supplementary system. This is an auxiliary system you can call, which is helping us pumping this fuel, into the engine. So what happens is basically, okay, I'll just tell you. What happens is basically, this particular pump, because we need to regulate the amount of fuel that is going into the engine and amount of oxygen is going into the engine, you will need the pump to pump it. Okay. And accordingly, you can regulate the amount of hydrogen is going. Again, you can't burn liquid hydrogen because it will not be able to create that much amount of efficient fuel. Okay, so you have to convert that hydrogen into its gaseous form. You need to raise its temperature in order to burn it. So once you pump this, there is, let's say this is the tank, this is the engine, and this is the combustion chamber. Okay, so what happens is, once you're from this pump, you are pumping the fuel, and you're basically not going directly to the engine. You're going around the chamber. Then you are basically injecting it into the engine. Okay, I'll also show you an animation of this. There I'll be able to better explain this concept to you all. So how this thing works. The basic concept is pump is needed to regulate the flow. Then your hydrogen needs to expand. It needs to gain temperature. It needs to be transformed into its gaseous form without losing pressure that it has, because once you spontaneously combust that highly pressurized, high pressure, high temperature fuel, you will get a high amount of thrust. So to raise the temperature, basically this chamber is very hot. Okay, so this chamber can generate up to 3000 degrees Celsius of a temperature, which is again which could again cause material damage. So that way you will need costlier components. But anyways, you will pass the hydrogen through over this by setting up a piping system or from over this chamber, which basically transfers the heat to the hydrogen, which basically makes it expand and transform from liquid hydrogen to a gaseous form. And then it is being provided to the engine, and there it is being burned. And it's not just about hydrogen, about the oxygen also. Same thing is being done. So then it is being mixed and it is being operated. There are a couple of ways to do this. Okay, so let's just see how things are going to go. So from start, you have your cryogenic engine. Okay, so just a minute. Okay, yeah. So this is your cryogenic engine. So this part right here that you can see is the auxiliary system of the pump and turbine system. Okay. I'll also address some of the key issues with that, like what is the key issues. But that is the thing. This is your hydrogen pump. Similar on the other side, you have your oxygen pump. Okay. So once that is being pumped, you see these pipings, right? Yeah, you see these pipings, right? So these are the pipings which are basically being provided. So this is the horizontal piping. These are basically provided to pass the liquid hydrogen and liquid oxygen through these, and they're raising the temperature, and again then they will be redirected to the engine. Okay. So this is the structure. So what exactly is done? Let me just show you. So in order to generate enough amount of action, you need enough amount of reaction, right? So for that, you will need to generate enough amount of thrust. So you can't just directly inject the fuel into this burning chamber, right? So all of these concepts I have explained. Yeah. Let's jump to, like, basically this is the facility. Okay, how these things are processed, how the hydrogen is basically liquefied. You have a series of compressors which compresses the hydrogen. Then you have condensers, you have throttling device. Then you basically collect your liquid hydrogen. Same thing you do with liquid oxygen. And then this is being transported with these big ass trucks to this chambers. So this is where your liquid hydrogen is being stored, or liquid oxygen is being stored. And before actually you're going to launch this vehicle into the air, you're just before that you're filling up these tanks. Okay, So it's stored over there, just that you are filling up this tank once you are ready to launch, or once you're preparing for the launch. Now, you need intense amount of insulation. Okay, so for that you will use this polyurethane, and it will be having a thick layer of polyurethane printed over this outer layer of the tank, so that it can be protected from the atmospheric heat. Okay, then once you burn this directly, if you burn this directly, the biggest issue with this is it won't be able to generate enough amount of thrust, because it won't be able to burn properly, because it is in this liquid state, right? So due to that, this is just one factor, but there are other factors also to this, due to which you need an auxiliary system. Okay, what sort of auxiliary system are we talking about then? A pump, right? But again, with the pump, you have a problem with electricity. So you use just an impeller. Now, in order to power this impeller, you need a turbine, because you need a pump and turbine arrangement. Turbine will rotate the shaft, in turn it will rotate the impeller, and accordingly you can pump the fuel out, and accordingly you can move forward. So this is the exact arrangement you're going to use. So when your liquid hydrogen is coming here, you are pumping it, and you are then supplying it. Okay. So again, once you supply it from there, what happens is, just a minute, let me just, okay. Yeah. So here, as you can see, your liquid hydrogen is coming here. Your chamber temperature is increasingly more. Okay. So basically, you're trying to convert that liquid hydrogen by passing it over this arrangement, and then coming to this point. Yeah, coming to this particular point from here, this is a liquefied form of that hydrogen, and then it is being transferred from here to again, like that liquefied hydrogen is controlling the turbine, and the turbine is rotating the this thing, your impeller, and then again it is being passed through the to the engine from here and being burned down. So whatever your liquid hydrogen is there, its gaseous format who is over here, that gaseous format is being used to control or rotate the turbine, which in turn rotates the impeller. Here again the same thing. If you are using the same fuel to control the turbine, which controls the pump operation, which in turn controls or regulates the flow, you need to have a highly precise amount of calculation to be done in order to make this system operable. Because if even smallest thing goes wrong, your fuel ratio becomes it becomes scrappy. Okay, so what do people do? This is the biggest problem with this kind of arrangement. Okay, if you directly do something like this, you are still unable to control the aftermath. If something goes wrong, then it is still again it will become very hectic process to control this the supply of the fuel. It might irregulate and it might damage the whole system, and your engine will fail. So what next? What are the ideas around this? So one idea would be to have a separate combustion chamber. Okay, so what this means is you will supply the liquid hydrogen from here and liquid oxygen from here. You will ionize it over here basically, and you're basically spraying particles and burning those particles. So once you burn this, still even if you're burning it, it's not completely getting burned because of the nature of it, because it is in liquefied format still, and you're sprinkling it. It will be partially burning. It will release some of the energy, but it will partially burn, and this exhaust then is basically being used to control this auxiliary system. Now this becomes an independent system because you're losing some amount of fuel, but that same fuel is not controlling the flow of the liquid hydrogen that is going into the chamber. Okay, it is a separate system. So once you separate these two, you are still losing fuel, but you are maintaining control over this auxiliary system. This is another drawback of this system, and even SpaceX uses this kind of technology to boost their Falcon rockets. But it's still, you are losing precious fuel in this process. So this particular cycle is called as gas generator cycle, because you are burning some amount of fuel to run this auxiliary system, and then you are supplying. So what you can do is then, instead of wasting that, okay, what you can do is you can just directly supply what this guy did is secondary system, or the better version of this system would be eliminating this exhaust. Like, don't put this half or partially burnt fuel into the air, but burn that fuel partially, redirect it to the chamber. Now here, what happens is, here your fuel gets partially burned, and then it is being used to power this turbine over here. And this partially burned fuel basically raises the temperature of the rest of the hydrogen that is there. Okay, and to a great extent. And that high temperature, high pressure, partially burned hydrogen is being completely burned in the chamber. Due to the temperature rising, your speed increases, your exhaust speed increases. So even though you are burning the fuel partially over here, you are compensating with that with the temperature. Remember the proportion that I have talked about, right? Your speed is directly proportional to your temperature. So so long as you are raising the temperature of the fuel, it is partially burnt. When it's going to get completely burnt, like before it's going to get completely burnt, it will become fuel rich over here. And that basically intensifies the process of burning the rest of the fuel, and generating the appropriate amount of thrust that we are going to need. Okay. And this is the secondary, this is the second cycle. This is called as, I think it is called as, staged combustion cycle. Basically, you are burning the fuel in two stages. So one is here, one is there. And you are not losing fuel, you are completely using it. So apart from this, okay, now these are the two cycles that are being currently used. Depending upon the applications, both the cycles are being used. Wherever it is necessary to use the gas generator cycle, it is used. Wherever it is necessary to use, or practically possible to use this kind of cycle, the staged combustion cycle is being used. Okay. Now, coming to this, how this fuel burns, right? So you will have an injector plate. You will have your oxidizer and your hydrogen. Their atomization is being done, and you have your pyrotechnic igniter, which basically burns the fuel, and you have your system. Okay. Now, in order to, again, your chamber generates as high temperatures as 3000 degrees Celsius. So in order to cool it off, right, in order to maintain the temperature of this outer layer, just a minute. This outer layer, this particular material, you are passing your liquid hydrogen, liquid oxygen through this. So essentially, your hydrogen is gaining heat, but also your chamber material is getting cooled off. So it's a give and take, and that's how basically you're maintaining, you're hitting two birds with one stone. So you're maintaining the temperature of this system also, and you are converting your hydrogen from liquid to gaseous state also. So when your oxygen moves something like this, it will move to the chamber. Then your oxidizer is again supplied over here, and it is being burnt and it is being processed. So there are different ways to do this. You can also pass your oxygen from this chain. You can directly inject your oxygen by doing that. So in the previous cycle, it is shown that your oxidizer is directly injected, and your fuel is then being converted into its gaseous format. So there are multiple ways to do this depending upon the application and intensity. To again boost the speed of the exhaust, you use something called as convergent divergent nozzle. So maybe you must have seen in aerodynamics that you have this convergent divergent nozzle where you are again reducing the throat area, and there you are increasing the thrust from here. You are basically getting additional thrust from here. So yeah, from here you are getting additional thrust. So that's how these are the things. That's how it is being implemented, and that's how it is being done. And there are only few countries that are being able to do this. Okay. So propellants mixture ratio is depending upon oxidizer mass upon fuel mass, and both the pumps are there. So as you can see, there is oxidizer turbo pump, and there is hydrogen turbo pump. So this is the actual arrangement that is being done. If you can see, so both your oxidizer and your hydrogen are being burned, and this is basically the ideal system where you are not losing any fuel. You are completely utilizing it, and you are completely burning it, and accordingly you are getting the highest amount of efficiency that you can get from this particular concept. The challenge with this kind of thing is still there. Even though you are able to control you are able to have some amount of control over this turbo pumps, over these combustion chambers, it's not complete control. Things still could go sideways. Okay, so some people, what they do is they use another auxiliary system called as like a gearbox. They use to keep the speed of the impeller and speed of the turbine separate. Because if you have, let's say, if you have over here, you are seeing that your impeller is basically rotating at the same speed at this turbine. So at any given moment of time, if your fuel enriched mixture reduces its speed, your pumping speed also affects due to that, right? So in order to avoid such kind of challenges, people use some kind of auxiliary methods like a gearbox to pump the fuel properly, to keep the both of the speeds separate, so that even if your turbine loses speed, your pump will not lose speed, and it will become sufficient. It will become self-sufficient in order for you to run. But still, this is the biggest challenge in creating a cryogenic engine that people are trying to figure out, because you need some kind of system to be able to have precise and manual control over it at all times. Second biggest challenge is thermal insulation of all the engine. As you can see, this is thermal imaging. The red part is basically highly is having higher temperature, and gradually it becomes blue. So blue is basically having lower temperature, comparatively lower temperature. Okay, so thermal insulation is biggest criteria, because again, you want to avoid material damage at all costs. So shouldn't happen that you need to have additional layers of insulation. You need to make sure that some of the critical parts that cryogenic engine has, you need to use expensive parts. You need to use titanium, aluminum alloys, such kind of parts you need to use in order to create this kind of engine, which are expensive again. And the third challenge is hydrogen embrittlement, okay? Because you are storing your hydrogen over here, it will again have effect on this tank, because you are operating at your hydrogen is stored at minus 253 degrees Celsius. So it's bound to have an impact on, bound to have a reaction on the storage material, storage tank. So again, that is your third challenge. So These are the reasons why most of the countries are not able to produce a sufficient enough cryogenic engine. There is a lot of research going on. Even we have something called Vikas, which was developed early in 1970s. Vikram Sarabhai developed that engine. It's a rocket thrust engine that has been developed to produce more amount of thrust, and it's still under development. There are different stages at which they're trying to improve the thrust efficiency to go into supersonics, to go into hypersonics, but it's still in the under process. So different launch pads, different satellites that we have launched using Vikas itself. So this is how the cryogenic engine is being operated, and these are the key challenges. So there is a need of working on these kind of challenges and how to make it functional and how to make it operable. So yeah, that's all about it. So all in all, in conclusion, we have seen rocket propulsion, we have seen fuel and oxidizer, we have seen specific impulse and what how the fuel is burned and what are the necessary aspects that we need to take care of. Then there are other mechanical design aspects that we need to take care of in terms of controlling the engine, in terms of making sure that your material doesn't get damaged. And there are a lot of things based on different applications, different cycles are being used and modifications are being done. And we have even seen why is it difficult to create this engine, right? Because of thermal insulation, because of being able to have precise amount of control over the pumping mechanism and like thermal, like hydrogen embrittlement of the tank. So these are just to name the few. These are just prime challenges. So yeah, that's about it. Now, if anybody has any questions about this, they can ask. I think people have put in. Okay. So Abdullah is asking, what is the role of CD nozzle here, convergent divergent nozzle? Yeah, it's basically being used for improvising the thrust, improving the thrust. Because see, you want more speed, right? So basic concept is, share my screen again. Okay. Okay. Basic concept is if you pass a fuel over here, it will lose its pressure, it will gain its velocity over here. And when you exit it from, when it is exited from here, it is going, it basically gets thrown back. Okay. So it basically gets thrown out. So due to that, your reaction force increases and basically you're able to generate more amount of thrust. So it's just an additional design change to the chamber, to the exhaust chamber. It is also called as flame holder or flame chamber, which is basically being used to contain the flame, contain the exhaust gases. And yeah, that's the only reason why a conversion diversion nozzle is being used. In IC engines, we learned about stoichiometry of petrol, diesel, 1 part of fuel plus 19-20 parts of air. Is it the same ratio in the rocket? I'm not sure about the exact ratio what they are using, but it's necessarily the mixture ratio depends upon oxidizer mass upon fuel mass. So yeah, how can we solve existing engine problem? Okay, that's an interesting question. The existing engine problem is the biggest problem that I see from mechanical perspective is.
Sir, existing engine means, sir?
Existing engine means like what is the current stage at the engine is. Like let's say we are using Vikas, right? Vikas is a type of engine that we are using. So if I show you. So yeah, this is the current engine that we are using. Okay, so as you can see, this is using gas generator cycle. As you can see, there is a separate exhaust so we are losing fuel, and we are powering this. Okay, so existing engine means that this is our existing engine, and what are the problems associated with that, and how we can tackle those, and how we can make it more efficient. Okay, so to be able to solve this problem, so there are a couple of things that we can do. First thing is using some kind of electronic control panel device. That could be one idea, but it again won't be able to sustain the amount of heat the the chamber has. So until and unless we have advanced enough material which can sustain that kind of heat, which can be used in electronics, create such kind of electronics, precise control of moving, like controlling the fuel. Until and unless that happens, we'll still need to rely on mechanical design, which is again using gearbox or using additional mechanisms to control the pump flow, or basically to separate the pumping mechanism and pumping speed and turbine speed, so that we can have more regulation over it. That is the current solution for that, but it still adds on weight. But yeah, so that is currently being under development, how to make it lightweight and how to even optimize that. So that's there. The rocket fuel, we can't use uranium as fuel due to the gas left over will be radioactive waste, and it can't roam around just like that, but we will use it in war rocket to make destruction. Even that is banned by the agency, we can't use. Yeah. But it's not about just a radioactive fuel. This what system that we have talked about is only one system, which is liquid propellant system or liquid propulsion system, because your storage is you are using liquefied and hydrogen and oxygen. There is solid rocket propulsion as well. So you are using solid fuel to initiate a chain reaction so that it can exert a certain amount of energy. That energy is being used to power up the different propellant engines, but it is still under development because it is the problem is same. The solid, the chain reaction that it produces, the amount of heat that it produces, and to convert that heat into ample amount of energy, you need devices like you need steam turbines, so that you can generate that amount of thrust, that amount of propellant force. But it's still under research. So yeah, that is still being experimented. Quite crazy question. Prasad says, if I want to learn about rocket engine practically, how I can start? Except books, like practically. The best practical way that I know is visiting ISRO to be able to actually understand, because there are these campaigns that ISRO does. Okay, you can check out their website, and even DRDO has these campaigns. What they do is what they do is they host these campaigns where you can go visit, you can go actually explore how these things are working in their own facilities. And there could be one thing, they do have their own examinations. If you get qualified through those examinations, you get direct entry, direct access to certain things, and you might even have some opportunity over there, being a research fellow scientist or something, where you get to work on things. But still, if you want to learn, the first thing you need to do is accept books, focus on articles, blogs, do a bit of a research on Google. Again, books are a necessary thing. You can't completely disregard books. You have to understand these sort of concepts. It doesn't come naturally. You need to, because the concept of convergent divergent nozzles, the concept of pump being operated by turbine using mechanical aspect, all of these things are in books only. Then they get to practical stuff, and then they are implemented. Books are necessary, but if you want to start use both the resources. Use Google as well as use your traditional books, and see their practical implementation. If you find some decent material like nice videos or something, you can get get more information out of it. So that's how it is. Even the best thing to do is talk to people who work in this kind of industries. They have some amount of time. Go explore that as well. Build your network. That will also help you out. You'll get exposure. You'll get opportunities. You'll get. So yeah, simultaneously you can do. The biggest thing you can do is just start learning, start exploring, and that way it will open up ways.
Exactly, sir. Thank you so much for your feedback. Or as you said, that books are very essential part. So
Hmm.
I really appreciate that. Exactly, this is basically a fundamental thing. But whenever we just basically try to get into ISRO's camping or DRDO's camping, they are just like I have visited once like DRDO, and
Hmm.
they told you some information about the engine. For example,
Hmm.
how Vikas engine developed, but they will not tell you how technically it works because it's basically intellectual property for the country, right?
Exactly.
So if
Exactly.
some people want to get into that technical stuff and have some plans, like next 5 years, 10 years, they will have some plans about to build something. Like I have
Hmm.
some plans. So how I can start? That was my question. So I get the answer. And
Yeah.
secondly, I want to ask if someone, for example, in foreign there is like rocket festivals, like
Hmm.
small like students and college youngsters will develop the rockets like made by 3D printing and solid rocket motors, and
Hmm.
there is multiple competitions. So like that, is there something in India also which you know? Because I try to find it, but I haven't get anything like practically happening.
For now, I don't think there is anything being done in India as such. If I have something, I'll put up a LinkedIn post so that you can see. But
Okay.
for now, I haven't came across. Oh, only thing is, yeah, the campaigns you are exactly right. They will give you only a limited amount of information, but it is up to
Exactly
you to
that.
interpret. So the biggest thing you can do is get access, like from if you are in a university, you might have some access to research papers or online documents which are publicly not available. Okay, because these citations are not publicly available. What they are working on
Okay.
technically. So if you have some connections with your university, if you can get access to that, like where you get reference books, similarly you get access to research papers. Go through those
Okay.
research papers, start understanding the technical aspects of, because in those research papers they have mentioned, like they don't mention like from everything from scratch. There will be information in bits and pieces, so you will need to use reference books, and you will need to understand like some of the concepts and piece it together to create your own understanding, and then deduce it, get it verified with your professors, with your with whomever your whomever your guide or mentor is, then understand the process and then take it further. So that is a biggest help for you if you are going to research, and if you want to go into deeper technical stuff. The first thing is research.
Okay. Okay, sir. Okay. And can you suggest some name of book like which have technical, which will best for the technical start? Like some books for the rocket science. There are multiple, but I don't know which book exactly will serve what I want.
I need to do a bit of research on that. You
Okay.
can get connected with me on LinkedIn. I'll let you know over there.
Sure, sir. Can I get your LinkedIn ID or contact number or something?
You
So
can just
that
Google it. You can just type in Hemant Fegade. You will find me over there.
Hemant?
Hemant Fegade.
Okay. Okay.
Yeah, yeah,
Okay, sir. Thank you so much.
yeah,
So,
yeah.
so I think the introduction to rocket engines is the best book for the layman engineer, such that understand the basic concepts of rocket and payload. And while I was in my college, I have taken the open elective. There I have read about this book, and the book is good. And comparatively, I have read the shade notes of my professor, and
Mhm.
with even though are good, and I have one doubt that actually you have clarified that doubt. My doubt was when they to read the history of at least to read the to know about the latest projects, then obviously we will refer the citations or refer the what we call the
Research papers.
right, research paper and journal papers. So by writing down the journal paper, doesn't they reveal the secrets of IP, intellectual property, or
Basically,
will they hide something secrets?
yes, they do. They do. They what they do is they write it in a
आणि आजच आत्ताच बाहेर काढले.
yeah, hi. So what they do is they put the information in a partial format, in incomplete format. Also, they do the second thing that they do is they put the information that is needed, but they write it in a way which is like in gumake they write it. So in a twisted word, they write it. So it's our for us to be able to understand. You need to read it through at least a couple of more times, and yeah. So that is the case. So when you are you're working with this kind of thing, you need to refer to citations, and yeah, you need to interpret that citation in a proper way. So that is the thing, and you can find easily on internet how to read a research paper. That's a great add-on you can do. Yeah. Has a liquid propulsion system been employed in some jet, marine, etc., apart from rocket? To exactly this kind of system is not implemented, because this is a very bulky system for even for jet engines. Jet engines have a miniature version of this, but it is again very complex. So that's a different thing, because you don't need, for jet engines to operate, you don't need that much amount of fuel to start with, to begin with. So the tank size, again, it's reduced, the operational, because you are refueling and all of that is there. So your flight time is also less. In rocket engines, your flight time is way more, right? So yeah, it depends on that. So yeah, I'm really sorry everybody, because I have somewhere I have to be. So I'll be taking your leave for now. And you guys can connect me over LinkedIn, not a problem. I'll resolve all of your questions over there as well. So have a nice evening, everybody. I hope it was a wonderful session for you. I had a great time. Thank you very much for being interactive, and thank you very much for keep on interacting. So I take your leave now. Have a nice evening. Take care. Bye-bye.